My name is Darren Hartl. I'm an assistant professor in the Department of Aerospace Engineering at Texas A&M University, and I'll be discussing our design, fabrication, and experimental demonstration of a shape memory alloy-based adaptive flow modification system. It is, I think, very important to mention that the entirety of this work, and largely the slides shown here, were created by two undergraduates at Texas A&M, and not only undergraduates but underclassmen. Kevin Lieb and Ryan Lotz were both sophomores in our department working in my lab, and so I'm very proud to be showing some of the preliminary development work that they've done. So stick around. So to overview the project, the goal was to demonstrate that an SMA torque tube could be used as an actuator for a low-speed aerodynamic application, where the demonstration was going to be performed at full scale, and the flow speeds and thus the aerodynamic loading was going to be greater than full scale. So demonstrated at full scale and greater than full speed. And so what was created was a split flap prototype, which was installed in our 3x4 foot low-speed wind tunnel in our department at Texas A&M. And various kinds of testing were going to be performed to assess in a preliminary sense the thermal response of the system, the SMAs being obviously thermally driven, the torque delivery capabilities, especially under very high aerodynamic loads, which we'll show later. The cycle times was of interest to those who commissioned this work, and then also actually look at airflow disruption using some metrologies that we have access to and are familiar with. This project, like the SMA morphing radiator also presented this year at SMASIS, this concept was enabled through the availability of shape memory alloy torque tubes. And so the company that's done the most in this area, though not affiliated with this project, is Boeing, who has flight tested shape memory alloy torque tubes on the clean adaptive trailing edge, where they had a small tab installed at the aft of a wing, and that was actuated by a rather small, a couple of dry erase marker sized set of SMA torque tubes. And then more recently in 2017, Boeing partnered with NASA to demonstrate the span-wise adaptive wing, in which SMA torque tubes were installed at the outer 3/4 span position and used to rotate the end of a wing of a 14-foot wingspan UAV to the positive 90 and negative 90 positions, and flat in between. So nearly 180 degrees, if I recall, actuation capability. So with these successful demonstrations, we knew we were in a good position to develop the flow disruptive application that will be shown herein. So the theory of operation basically is that there is a plastic ABS printed body, here shown in dark gray actually, that will represent the static portion of the flow disruptor, or the split flap application. And then to get a very particular contour, a very precisely milled aluminum flap was then installed that lays flush into a void in the 3D printed ABS. That flap is driven by a nickel titanium torque tube, which is embedded in the flap at its root and then terminates at an aluminum shoulder. Kind of shown in section, kind of the flip view of the below. Here we have the flap. The SMA torque tube is installed using simple steel dowels at the end. There's a cartridge heater installed in the middle of the tube that's going to provide the heating. Cooling is, of course, provided by heat leaving the SMA and conducting into the very highly thermally conductive aluminum flap. At the root, this is all terminated again into a strong aluminum shoulder. In this picture at the top, the ABS plastic fixed portion is removed for clarity. There will be other metrologies, including a torsional load sensor and a rotational potentiometer that will allow us to measure the force being generated and the rotation being generated. And so as we heat the SMA tube, it twists in such a way that the flap deploys out of its stowage position towards the flow. So the flow would be coming this way, flowing as my arrow is pointing. The flap deploys against the flow at a substantial torque load being generated back onto the SMA tube. And then as the SMA tube is cooled, the flap lays back into the recess, into the fixed portion of the flow disruptor. So relatively simple SMA operation. Heat it up, cool it down, it moves. But again, under very high loads and all created at full scale. So some of the metrologies and inputs. So to provide the heat to the SMA, we've got a 120 volt cartridge heater, which the power will be provided to this heater through a solid state relay. And so our signal is going to be a pulse width modulated signal of 120 volt AC. So I guess a pulse width signal of a AC current. And the duty cycle of that pulse width modulated signal that's basically supplied to the relay and thus to the cartridge heater would be determined by a simple PID controller. Measuring the torque is a home-built load cell, and which was calibrated, and then a single-turn rotary potentiometer would give us our angle measurements up to 90 degrees at maximum. Not pictured are the two thermocouples that were used to measure temperature, as well as a thermal camera, which will show the results from that. And we used a hot wire anemometry system to look at flow disruption, so the vorticity in a preliminary sense, I should say, behind the flow disruptor in the deployed and undeployed condition. Again, do keep in mind that everything you see here was done by two sophomores, I think, with a very promising future in research in aerospace. So the measurements were all taken in our 3 foot by 4 foot tunnel, which is managed by my lab, so it's in my facility. This has a 50 meter a second or 110 mile an hour maximum flow speed. Our tests are going to be up to 40 meters a second or 90 miles an hour, which was indicated by our collaborators, uncredited collaborators, as being well above the speed needed by the application. Here we have a video of the deployment cycle. Now this is shown at 10x speed. We'll talk about deployment and retraction time later in more detail, but you get an idea, and this is, I believe, a 60-degree deployment example. So you see that it deploys and then retracts. You see, of course, that it deploys much faster than it retracts. It's easier to heat a metal than to cool it, and that's obvious for those that have worked with SMAs or gotten metal hot at all. But this gives you an idea. Obviously, the actuation is incredibly smooth, and this also lets you see how the aluminum deployable portion of the flow disruptor is kind of embedded into and lays into this 3D printed portion, static portion. So diving into the data, and again, basically the idea was to get a survey of results across different mechanisms and physical fields to get a good understanding of this system towards probably more applications testing. But here you see, for example, the torque, the internal temperature near the cartridge heater, the external temperature on the outside of the aluminum flap, the deployment angle, and the power percentage all shown on one plot. And so you see the units here, they all can be collapsed down to one y-axis given these change in units. And what was performed here was the flap was deployed, looking at the purple, to a command of about 30 to 30 degrees, and then the flow speed was first set to 80 miles an hour, 35 meters a second, and then slightly oscillated, and the ability to maintain position under a change in the applied torque was assessed. This was also repeated at a 45-degree deployment situation. So, of course, you can see the power, which is basically the duty cycle for the pulse width modulated system, changing as needed to maintain a very stable deployment angle. That's the purple line. Also note that the torque is at the 45 degrees, for example, up to and exceeding 50 inch-pounds. So this is a not insignificant amount of torque that the SMA is taking. And in fact, the limiting factor is not the SMA torque tube, but more elements of the assembly and connections. So this kind of data was taken for a number of speeds and a number of deployment angles. It's worth mentioning, I discussed the peak deployment torque at 40 meters a second, which is about 90 miles an hour local velocity or inlet velocity, that you're looking at a full 70 inch-pounds of torque on the being supplied to the SMA torque tube, or having to be maintained by the SMA torque tube. And this was nowhere near, we don't have it noted here, but it was nowhere near the limits of the torque tube, even at this 90 miles an hour. So after those original tests, we noticed that the cycle time was actually quite high. And one reason for that, if I click through the animations, is that there was a sleeve placed on the outside of the torque tube. And one idea essentially was to get the heat out of the torque tube into the aluminum flap, the movable flap. The problem with that, of course, and we'll see in a minute, the two times relative to each other, deployment versus retraction. By having a highly conductive path, it becomes very difficult to deploy the flow disruptor, because convection, especially at 90 miles an hour, is pulling the heat off of that flap very, very quickly. It's an aluminum flap. And so it's conducting heat very well. It's being convected away. So then we looked at replacing this aluminum sleeve with a G10, essentially a glass fiber composite phenolic type material, which greatly increased the thermal insulation of the tube. And that overall, the overall cycle time was greatly reduced when we went to this alternative system, which is, of course, the purpose of R&D, is to notice things like this and then make corrections. And Kevin and Ryan were fantastic at doing this. So then, given that, we could look at the deployment time at up to two different deployment positions, 30 degrees and 45 degrees, at different velocities. And so again, deployment time is basically actuation time upon heating. And of course, we see that as we increase velocity, we increase convection, which makes it harder to heat the tube to a given temperature needed to deploy to a given position. And so the deployment time goes up. It also takes longer to deploy 45 degrees than 30, because you have further to go. The SMA needs to get hotter. You have the opposite story upon cooling, of course, because at higher speeds you convect away more heat again, but that helps in the cooling process. And so we're able to actually drop the cooling time quite a bit at higher speeds. Again, 45 degrees deployment taking longer than 30. And so we have this characterization data, again, across multiple speeds, at multiple angles. We're looking at actuation and deployment speed, all things that our uncredited collaborators were very interested in. We also could look at the temperature profiles on the exterior of the device. This is a piece of tape added to the aluminum flap to help, of course, with emissivity and provide good thermography data. And that lets us see the temperature profile as we get away from the ABS well into the aluminum flap, where more and more convection is allowed to carry more and more heat away. And so another number we needed to know was, what is the peak temperature that we're seeing? And we're seeing at most 67 C at zero velocity. So this is when there's no active forced convective cooling. We only get to 67. Even maybe more importantly is that the ABS body never exceeds 54 C. And so while we were obviously, for this case, watching the max temperature of the ABS, it's envisioned that the final application would obviously be built by more thermally robust, built using a more thermally robust material. And finally, as a bonus metrology, the students prepared a wire anemometry system that looked at the percent turbulence. So this is all kind of shown to scale with the flap here behind the flap in its retracted configuration, and then in its deployed configuration. Note that the percent turbulence scale is the same, and so you're seeing a very apples and apples comparison to the vorticity or turbulence field behind the flow disruption device, whether the movable flap is deployed or retracted. And so again, kind of at scale relative to this picture. So great bonus results. So to conclude, an SMA torque tube driven flow modification system was designed, built, and demonstrated at full scale and under aerodynamic loads exceeding those expected in the application. Issues of rate, stability, and airflow disruption were assessed in a preliminary manner, and the testing as installed in the final application is expected to commence as soon, basically, as COVID-related travel restrictions are lifted. Thank you.